Hello, my dear students. Today I am here to discuss bending stresses in beams. In this chapter, today I am going to derive the bending equation, which is also called the flexural equation. So what is that equation? The equation is m upon I is equal to sigma b upon y is equal to E upon R. This is called the bending equation or flexural equation. Now, what does this terms actually means? M, it is the maximum bending moment, or it is also called the moment of resistance. And I is the area moment of inertia. E is the modulus of elasticity. Sigma b is the bending stress. Y is the distance of fiber or a layer of the section from the neutral axis. R is the radius of curvature, and E is the modulus of elasticity. Now, before going for derivation, we have to understand, or we have to know few assumptions that will be used in deriving the equation, or we can say the assumptions made in theory of pure bending. The very first assumption is the material is homogeneous. Homogeneous means the material is of same kind. The material that we will take, or the section that we will take, it will be of same kind, and it is isotropic. That means the elastic properties in all directions are equal. The second one is the transverse section which were plane before bending will remain same after bending also. That means the section that we will take, it will remain plane before and after bending. There will be no radial strain, only longitudinal or linear strain will occur. Means in terms of radius, there will be no strain. Neutral axis will remain same before and after bending. That we already know from the definition of neutral axis. It is the axis which remain same before and after bending. The last one is the beam is initially straight and all longitudinal fibers bent into circular arcs with a common center of curvature. So these are the assumptions that we will use while deriving the bending equation. Now, see, let us consider A, B, C, D, a small section having length dx. So this length is dx of a beam subjected to a bending moment M shown in figure. So this is the bending moment. This is a second bending moment applied on the section. NN is the neutral axis since it is a rectangular section. So at the mid of the section, there is a line NN, and that is called the neutral axis. EF is a layer. EF is a layer at a distance of y from the neutral axis. So this distance is y from the neutral axis. Now figure 2, this figure is the deformation of dx length after bending. Means this is the before bending, and after bending what will happen, this A, B, C, D will be converted to A dash, B dash, C dash, D dash. That means the top layer is under compression and the bottom layer is under tension. Then NN become N dash, EF become E dash, F dash, Y becomes Y. Why? Because here is the assumptions we are using. There will be no radial strain. Radial strains are not there, so Y will remain same. And another assumption, that is the neutral axis will remain same before and after bending. So NN will also be equal to N dash, N dash. These assumptions here I have written. EF equal to NN, EF is equal to NN is equal to DX is equal to N dash, N dash. These assumptions. Neutral axis will remain same before and after bending. Now there are some mathematical considerations are there from the figure 1, not figure 2. This is figure 2. From figure 2, n dash. So n dash is an arc which makes an angle theta at the center with radius of curvature r. So we can say that n dash is equal to r theta. And also n dash is equal to nn. N dash is equal to nn because neutral axis will remain same before and after bending. And from the figure 1, we can say that nn is equal to ef. So nn is equal to ef. And what is E dash F dash? So E dash F dash, again it is a arc makes an angle theta at the center of curvature with radius r plus y. This is r plus y. So E dash F dash is equal to r plus y multiplied by theta. Now we'll do the calculations on the fiber that we have taken EF. So first of all, we will find out what is the strain on the layer EF. So strain on layer EF. So earlier it was EF before bending. After bending, it becomes E dash F dash. Then what is the change? Change is E dash F dash minus EF. E dash F dash minus EF divided by original. Original is the EF. We have the values of E dash F dash as r plus y theta, minus EF. EF is r theta divided by EF. EF is r theta. So after simplification, we are getting strain on EF layer is y upon r. That means the strain is directly proportional to the distance from the neutral axis because r is constant. R is constant, so strain in a layer is directly proportional to the distance from the neutral axis. That is, the strain variation is linear. So this is one conclusion. The variation of strain is linear in case of pure bending. Now, stress variation. How the stress varies. Let us consider sigma b is the bending stress on the EF layer. E is the modulus of elasticity of the material. Then we can say E is equal to stress on layer divided by strain on the EF layer. So stress on the EF layer, we have taken it as sigma b. And what is the strain on the EF layer that we have already derived? The strain is equal to y upon r. So I am getting E upon r is equal to sigma b by y. This is the equation 1. From this, I am getting sigma b is equal to E multiplied by y divided by r. Again, see here, sigma b, that is the bending stress, is also directly proportional to the distance from the neutral axis because E is a material property, it is a constant, and r is the radius is also constant, and stress in any layer is proportional to the distance of the layer from the neutral axis. So just like strain, stress variation is also linear. So strain is also linear, stress is also linear. Now, let us consider dA is the area of the elemental length EF. Then what are the forces on the layer? Force is nothing but stress on EF multiplied by area EF. What is the stress? Stress is sigma b, area is dA. What is the value of sigma b? Sigma b is E upon E multiplied by y divided by r. So I put it here, E y divided by r multiplied by dA. So I am getting E by r multiplied by y dA. So if I want to find the total force on the section F, and that force is parallel to the section, so we can call is at shear force because it is parallel to the surface, so it is a shear force. So shear force F is equal to E upon I r integration y dA. And for pure bending, the shear force is 0. So I put F is equal to 0 means E upon r integration y dA equal to 0. Now, E upon r cannot be 0 because these are the constants that cannot be 0. So that means integration y dA must be equal to 0. And what is integration y dA? It is the moment of entire area of the section about the neutral axis. Moment about the neutral axis. What is this? The centroid. We know that moment on any area about an axis passing through its centroid is equal to 0. Moment on any area about an axis passing through its centroid is equal to 0. Means if the axis passing through the centroid, then the moment of the area about an axis is equal to 0. Hence, we can say that the neutral axis coincide with the centroidal axis. Thus, in pure bending, centroidal axis of a section gives the position of the neutral axis. So these questions may come. He proved that the centroidal axis gives the position of the neutral axis. So this complete your answer. Now we will find out the moment of resistance. And what is moment of resistance? See, due to pure bending, the layers above the neutral axis and below the neutral axis will be under tension and compression or vice versa, and that depends on the applied moment, whether the moment applied is hogging or sagging. Now, due to these stresses, what will happen? The forces will act on the layers. Forces will act on the layers, and this force will have a moment about the neutral axis. Now, the total moment of these forces about the neutral axis for a section is known as the moment of resistance. So how will you find the moment of resistance? We know the force on the layer EF already we know is E upon R Y dA. And if I want to find the moment about the neutral axis, I have to multiply it with Y. So force multiplied by Y. So I am getting ultimately E upon R Y squared dA. Now if I want to find the total moment of the forces about NA, I have to integrate this equation. So total moment is M is equal to integration E upon R Y squared dA. Take E upon R outside because it's a constant. So inside the integration term Y squared dA. And what is integration Y squared dA? Already we have learned integration Y squared dA is the area moment of inertia of the section about the neutral axis, which is denoted by I. So I can replace this integration Y squared dA as I. So I am getting M is equal to E upon R multiplied by I. Hence, M by I is equal to E upon R. This is equation number 2. Now, in the equation 1, we got E upon R is equal to sigma B upon Y. And here we are getting M upon I is equal to E upon R. So, from equation 1 and 2, M upon I is equal to sigma E upon R is equal to sigma B upon Y. This is called the bending equation or Flexural equation. So with this, I have completed the derivation of bending equation or Flexural equation. For any doubt and any queries, you can mail me. Thank you very much. Please share my video. Thank you.